Hello, and welcome to Curing Amnesia and Other GPU Maladies with AMD Developer Tools. This is the first of 3 presentations that cover the Radeon GPU Analyzer, the Radeon GPU Profiler, and our latest tool, the Radeon Memory Visualizer. This presentation focuses on the recent improvements to the Radeon GPU Analyzer and its support for DirectX 12. It was authored by Amit Ben-Moshe, who is the team lead for the product, and is being presented by myself, Gordon Selly. The Radeon GPU Analyzer, also known as RGA, is a shader programming tool that provides visibility into how high-level source code translates to GPU machine-level instructions and the static hardware resources it consumes. With RGA, you can generate ISA disassembly for AMD GPUs, as well as generating the intermediate language disassembly for the relevant compiler toolchains. RGA retrieves the hardware resource usage information for vector and scalar register consumption, register spills, local data share allocation, and scratch memory usage. RGA can also run static analysis algorithms on your code. The live VGPR option allows you to track register usage line by line throughout the assembly code. In addition, it is possible to build a control flow graph for your code. The tool is independent of the installed GPU, which means that you can analyze your code for any of the supported GPUs without having it present in your machine. RGA runs on both Linux and Windows and supports multiple graphics and compute APIs. RGA has been integrated into other shader tools, which use it primarily as a standalone compiler for HLSL, GLSL, and SPIA-V code. In this screenshot, you can see the Shader Playground tool, a website for exploring shader compilers. In this example, RGA is being used as a standalone compiler for the HLSL input code. Before we start talking about RGA for DirectX 12, I want to mention some of the other improvements that we have made in the last year. In March last year, we introduced a new UI support for Vulkan and changed the underlying compilation model. Instead of using a custom-made compilation path, which was tailored for the tool and made static assumptions on things like the API level state, this time we developed a driver stack that allowed us to leverage the same compilation path that is used by the driver in real life. This results in what you see is what you get. You get the closest disassembly and resource usage to the real-world scenario and can therefore make better optimization decisions. Another benefit of the new approach is that the compiler gets updated with new driver updates, so you don't need to wait for a new version of the tool to analyze your shaders with the most recent compiler. Let's have a look at some of the key features of the new UI. There is a source code editor in which, in addition to GLSL, you can edit SPIA-V binaries. When you drop a SPIA-V binary into the app, it is disassembled, and as part of the build, it is reassembled. You can use the pipeline state editor to change the Vulkan API level pipeline state. This, together with the shaders, is then used in the compilation process. After the pipeline is built successfully, you will see the disassembly in a dedicated view with the instructions color-coded by their type. For instance, memory instructions are colored in red to help identify areas with high memory pressure when quickly skimming through a long disassembly. The hardware resource usage statistics are displayed in a single line at the bottom for easy viewing. When a resource reaches or exceeds its limit, that item is highlighted in yellow, and a warning is displayed to indicate the potential performance issue. For example, as we can see in this screenshot, there are VGPR spills, scratch memory had to be used, and the code did not fit entirely into the instruction cache. And finally, this is how all the pieces come together in the new UI. In the last year, we extended RGA to support the new RDNA architecture that is used in the Radeon RX 5000 series GPUs. We also extended RGA to support DirectX 12, adding compute support in RGA 2.2 and graphics support in RGA 2.3. In general, DirectX 12 support in RGA is at the command line level. Like RGA's Vulkan support, it is built on top of the new RGA driver stack that provides real-world results, allowing you to make better optimization decisions than before. All of RGA's existing features are enabled by the new RGA driver stack. The new stack also allows you to target a specific AMD GPU without it physically being installed in your development rig. To compile DirectX 12 compute pipelines in RGA, we need two inputs, shaders and root signature. Both shaders and root signatures can be provided in two forms. Firstly, for HLSL source code, RGA will perform a front-end compilation. In cases where the shader model is 5.1 or above, DXC will be invoked to perform the compilation. RGA ships with a specific version of DXC as part of the package, but you can also plug and play your own version of DXC using the DXC option. Secondly, for DXIL or DX bytecode binary, no front-end compilation is performed, and the binaries are passed directly to the back end. Since root signatures are a new requirement for RGA, let's have a deeper look at how they can be provided to the tool. There are three main scenarios with root signatures. In cases where the root signature is defined in a macro definition in the HLSL code, and the root signature attribute is mentioned above the relevant compute shader referencing the relevant definition, you don't need to do anything. The root signature would be automatically detected and compiled as part of the front-end compilation of the shader. If the root signature attribute is not used for the compute shader in question, you can still make it work by passing the RS macro option with the macro name as the argument. In this case, RGA performs a two-pass compilation, first to compile the root signature and then to compile the shader. If the root signature is pre-compiled into a binary, that's even easier. Just use the RS bin option with the full path to the binary file as the argument. Just to get a sense of how simple it is to compile a DX12 compute pipeline in RGA, let's break down the invocation command. Assuming that the root signature is defined in the HLSL code and that the attribute is decorating the shader, the following arguments can be used to customize the compilation. No argument is required for the root signature in this example, but as explained earlier, you can use the RS macro or RS bin option to specify the root signature. Let's do the same for the DX12 graphics pipeline. It's almost the same as compute, but one thing is missing. Let's look again at the compilation process. On the right-hand side, you see the D3D runtime block, which we did not discuss for compute. The interaction with the D3D runtime happens through the DX12 backend executable, which is provided by RGA to perform the compilation. The DX12 backend is essentially a generic DX12 app. It accepts the DXIL and DX bytecode binaries and compiles the pipeline. This is fine for compute, but for graphics, just the presence of shaders and root signatures are not enough. A subset of the graphics pipeline state is also required. The vehicle through which we communicate the pipeline state to RGA is the GPSO file. This file defines the minimum required subset of pipeline state that is absolutely required for successful compilation with accurate results. You can generate a template GPSO file using the command line tool. It is text-based, easily editable, and has been designed for easy copy and paste of your source code. Let's go over the GPSO file structure. Firstly, the schema version is internal to RGA and used to track the version of the data structure. This is followed by the layout information, which includes the number of elements, followed by the descriptions of the actual elements. Next, we must define the primitive topology type, followed by the number of render targets and their render target view formats. These are needed to make sure the pixel shaders produce the correct disassembly. To summarize, we need three things to compile DX12 graphics pipelines using RGA: shaders, root signatures, and a GPSO file with pipeline state subset. That's it. It's that easy. So let's wrap it up there. Thanks for watching, and you can find out more about the Radeon GPU Analyzer on GPU Open and download it directly from GitHub using the links below. This is the second of three presentations that cover the Radeon GPU Analyzer, the Radeon GPU Profiler, and our latest tool, the Radeon Memory Visualizer. This presentation focuses on the recent improvements to the Radeon GPU Profiler, also known as RGP. It was authored by Chris Hezek, who is the team lead for the product, and is being presented by myself, Gordon Selly. RGP is a profiling tool for AMD GPUs. RGP uses low-level hardware features to visualize detailed timing information on the execution of graphics and compute workloads in an application. RGP can help you identify performance bottlenecks in your applications and also helps to bridge the gap between the graphics compute APIs and their final execution on the GPU hardware. We provide versions of RGP that run on Windows and Linux, and we currently support Vulkan, DirectX 12 and OpenCL applications. Let's review the original features of RGP as they were at GDC 2019. RGP is made up of two types of data views. Firstly, the overview windows give you high-level information about your application, and secondly, the event-based views give you a low-level look at how your workloads are executing on the GPU. We'll start by looking at the overview windows. First is the frame summary view. This is the only view in RGP that visualizes several frames worth of data. All other views in RGP are focused on the detailed events data collected in a single frame. The main area of interest in the frame summary page is the system activity timeline. The timeline is divided up into multiple sections, with a section dedicated to each queue that is created by the application. In this screenshot, we see that the application has created a graphics queue, a compute queue, and a copy queue. Within each queue, you can follow the lifetime of command buffers from submission time on the CPU to when they are executed on the GPU. In the system activity view, we can see that one frame has a light blue background. This frame indicates which part of the application contains the detailed profiling data that is used in all the other views in RGP. Although not shown here, this view can also display synchronization objects in the form of signals and weights. Next, we have the barriers view. Barriers can be one of the trickier things to get right when using DX12 and Vulkan. This view provides a list of all the barriers contained in the frame. For each barrier we show the duration, time spent waiting for previous work to finish, and as well as an indication of which part of the pipeline a barrier is waiting for. It also provides details about any layout transitions associated with the barrier, whether the barrier caused any cache invalidates or flushes, and whether a barrier originated from the application or the driver. Here we see the context roles view. Context rolling is a hardware feature specific to RDNA and GCN architectures, and needs to be taken into consideration when optimizing draws for AMD GPUs. Each draw requires a set of hardware context registers that describes the rendering state for that specific draw. When a new draw that requires a different render state enters the pipeline, an additional set of context registers is required. The process of assigning a set of context registers is called context rolling. A set of context registers follows the draw through the graphics pipeline until it is completed. On completion of the draw, that associated set of registers is free to be used by the next incoming draw. On AMD GPUs, there are 8 available sets of context registers, of which only 7 are available for the draws. The 8th is reserved for the compute dispatches. A worst-case scenario would occur if 8 subsequent draws each require a unique set of context registers. In this scenario, the last draw would have to wait for the first draw to finish before it can use the context registers, causing a stall. The context roles view can let you know if you're oversubscribing the set of available contexts. It can also help you optimize the use of context in your frame by letting you know which part of the hardware context are causing the context roles, and whether any context roles are partially or completely redundant. Next, we have the most expensive events view. This pane is fairly self-explanatory. It gives you a list of events sorted by the amount of time taken for each event. It can help you determine which draw calls you may want to focus your optimization efforts on using other parts of the tool. To wrap up the overview panes, we have the render and depth targets view. This view shows you all the color and depth targets used by the frame. At the top of the view, we can see that the timeline shows you which targets are active and at which points in your frame. The tree view at the bottom gives you more information about each target, including the format, dimensions, whether compression is enabled, and the number of events which output to the target. Now let's take a quick look at the events view in RGP. First up is the wavefront occupancy view. This view is a core feature of RGP. Displayed at the top of this view, the wavefront timeline gives a visual representation of the amount of wavefronts in flight throughout the frame. Bars extending up from the midline represent work coming from the graphics queues, while the bars extending down represent work coming from the async compute queues. This gives you a visual indication of how busy your frame is keeping the GPU. It can help you to determine where you might want to place the asynchronous compute work. For example, where you might have undesirable stalls, which might be represented by gaps in the timeline, or where you have workloads that result in low wavefront occupancy. The bottom half of the view contains the events timeline. This allows you to see the parallelism in your frame and allows you to correlate wavefronts in flight with draw calls and other events in your frame. Both the wavefront occupancy timeline and the event timeline support display modes to allow you to visualize the profiling data in different ways. On the right-hand side of the view, detailed information about the selected event or events is shown. Next, we have the event timing view. This view displays all events in the frame along with the timing data for each event. The tree view on the left can be configured to group the events by different categories, and the events in the timeline can be colored by different elements to help you gain insight into the events. Finally, we have the pipeline state view. For any given event, this view shows the parts of the pipeline that are used by that event. You can click any of the active pipeline stages to see more information about the activity in that particular stage. In the above screenshot, we have selected a dispatch event, which obviously only uses the compute shader stage. Details about the compute shader are displayed, including the number of threads, the wavefronts launched, as well as the usage of per wavefront resources like vector and scalar registers and local data share. So that was a quick look at some of the features in RGP as they stood at the time of GDC 2019. Since then, the team has been busy adding new functionality to RGP. Let's take a look. One of the major features that was added in the past year was support for the new RDNA architecture, which debuted in our RX 5000 series GPUs. The features that you've come to rely on in RGP are now supported in our latest GPUs. There are a few places where the UI has changed to adapt to the new RDNA architecture. Here we can see the new RDNA PrimS and Surface hardware shader stages that have been added to the wavefront occupancy timeline and event side panel. When running on RDNA hardware, the RGP UI will also show you if a shader was compiled in Wave32 or Wave64 mode. Here we can see a pixel shader that was compiled in Wave64 mode and a vertex shader that was compiled in Wave32 mode. We've also updated the barriers view to account for the additional cache level present in the RDNA hardware. Here we can see that the summary information at the top, as well as the invalidated column, will show information for the L0, 1, and 2 caches. In addition to adding support for RDNA, we've added several new features to help analyze pipelines and shader execution in your frame. We've added a new overview pane that focuses on pipeline usage. This view gives a summary of all the pipelines used within the frame. It shows the shaders contained in the pipeline as well as statistics for both the individual shaders and the pipelines themselves. This allows you to easily identify expensive shaders and pipelines. It also provides a list of events that use each pipeline, allowing you to quickly jump to those events in other views of RGP. We've also enhanced the pipeline state views to display the shader ISA code for any pipeline stage. As seen here, the pipeline state view has a new tab which contains the ISA code generated for the selected shader. At GDC 2019, we showed a preview of our new instruction timing feature. After a few design iterations, we released RGP with the version shown here. With this view, we can correlate the detailed low-level timing data from the hardware with the ISA instructions for a specific shader. This allows us to display where potential bottlenecks exist in the execution of the shader code. The instruction timing view assigns an instruction issue latency to each instruction. This latency represents the time difference between when the current instruction is issued and when the next instruction is issued. In the above screenshot, we see several buffer load instructions with a single clock issue latency. This is the ideal case on RDNA hardware where instructions can be issued on each clock cycle. However, we also see two instructions with larger reported average latency. These instructions are wait instructions, which represent synchronization points in the shader. In these cases, the shader is using these wait instructions to ensure the preceding load instructions are completed before moving on to execute additional instructions. By examining the latencies for a given instruction in a shader, you can gain insight into how the compiler takes your high-level shader code and translates it to machine ISA, and then how those instructions are executed on the actual hardware. The goal is to provide information you can use to modify shaders to try and achieve higher performance. In addition to the instruction timing information, this view also shows statistics about the shader execution in the side panel. Here we can see those statistics, which include an estimate of the functional unit utilization. These are the bar charts shown on the left here. It also gives a breakdown of the types of instructions executed, as well as some information on timing, number of wavefronts, and branches executed. These are seen on the right-hand side. Due to the high volume of detailed data required to support the instruction timing view, you must explicitly enable collection of this data for a given pipeline. Let's take a look at the typical workflow involved with collecting this data. First, you would use RGP to identify the shader of interest. This can be done, for example, using the most expensive events pane. Once you've identified the shader, the RGP UI will show you the API PSO hash for that shader. The API PSO hash is displayed in the side panel in the wavefront occupancy and event timing views. Clicking on the clipboard icon next to the API PSO hash copies the value into the clipboard. Next, we use the Radeon Developer panel to collect a new trace, which includes detailed instruction timing information for events which use the API PSO hash you identified in Step 1. On the Connection tab in the panel, click the Edit button to open the Profile Configuration dialog. For the instruction tracing setting, select API PSO and then paste the hash from the clipboard. Then relaunch your game and take a new capture. Then simply open the new capture in RGP and you're ready to start analyzing the instruction timing of your shader. In addition to displaying shader ISA and allowing you to get timing data for the ISA instructions, RGP has a few other display modes that help you analyze pipeline-specific data. Here we see that you can group events by their API PSO hash. When doing this, the event tree view contains top-level tree nodes for each API PSO hash. Each event that uses that API PSO is displayed as a child node in the event tree. There are also two new color by modes. Here we have selected color by API PSO so that the events are colored according to the API PSO hash used by the event. And here we see that events are colored by whether the event has detailed instruction timing data, which can be viewed in the instruction timing view. Events displayed with a light blue color are the events that have detailed instruction timing data. Another new feature added in the last year is the support for displaying what we call overlays in the event timeline in the wavefront occupancy view. As shown in this screenshot, there is a new overlay menu available at the top of the timeline. With this menu, you can enable 4 different overlays: user events, hardware contexts, command buffers, render targets. Each of these can be used to get a better understanding of the structure of your frame. So let's wrap it up there. Thanks for watching, and you can find out more about the Radeon GPU Profiler on GPU Open, and download it directly from GitHub using the links below. This is the third of 3 presentations that cover the Radeon GPU Analyzer, the Radeon GPU Profiler, and our latest tool, the Radeon Memory Visualizer. Also known as RMV, the Radeon Memory Visualizer is a product of many teams at AMD, and I want to thank everyone who's contributed to the creation of this capable new tool. I'm very excited to have the opportunity to introduce you to RMV, and I hope you find it as useful in analysing the memory usage of your graphics applications as we have. With the introduction of DirectX 12 and Vulkan, it has become necessary for developers to understand how their usage of the explicit APIs translates to actual activity on the GPU. This is a basic requirement in order to understand how to optimize for the modern GPU hardware. With the release of the Radeon GPU Profiler back in 2018, it became possible to visualize GPU activity in an actionable way at the API level. RGP is particularly helpful when it comes to understanding command buffer usage, overlapping workloads in graphics and asynchronous compute queues, scheduling synchronization objects, understanding the effects of barriers, and detecting context role stalls. More recently, RGP has been able to reveal individual shader instruction timings and latencies, allowing you to understand unit utilization and detecting shader bottlenecks. However, a fundamental aspect of GPU programming has been missing from RGP, and that is the ability to quickly and easily analyze an application's memory usage over time. The Radeon Memory Visualizer has been designed to fill this gap. Put simply, RMV tracks the allocation lifecycle information of an application's GPU memory resources and presents this information in an easy-to-understand form. RMV works in a similar way to RGP. A control panel is used to signal to the driver when to start and stop tracing the memory activity in a game, and then the data is presented using a dedicated visualization tool. Like RGP, RMV works in local and remote scenarios, and its underlying support is present in the public Radeon driver. Currently, RMV supports DirectX 12 and Vulkan applications on Windows. One of the key differences between RGP and RMV, and the prime reason that they are separate tools, is that RGP focuses on one frame's worth of low-level GPU data, whereas RMV is designed to trace memory usage over much longer periods of time. This is essential when you consider that the developer needs to understand the full life cycle of the resources in their games. It is important to remember that RMV does not record memory contents. It is not a memory debugger. Compared to RGP trace sizes, RMV memory trace files are small in comparison. A single RGP frame can contain hundreds of megabytes of data, but even long RMV traces are seldom more than a few tens of megabytes. Like its older sibling RGP, the Radeon Memory Visualizer was designed to answer very specific questions about how GPU memory is used in your application. Some of these questions are fairly simple in nature, but detailed answers are difficult and time-consuming to come by without a dedicated tool such as RMV. For example, how much VRAM am I using at any particular time? Am I close to oversubscribing? Which are my biggest resources and allocations? How efficiently am I sub-allocating? When was a specific resource uploaded? Have I leaked any resources or allocations? Are there unbound or unused resources? In which memory heap did a resource end up? Or did I simply forget to unload resources? Let's see how we can answer some of these questions using RMV. Let's take a look at an RMV trace from a typical game-like application, and I'll talk you through the key features of the tool and show you how we can answer some of these questions and more. When an RMV trace is loaded, the UI opens in the timeline view. Looking at the timeline along the top, we can see in this example that a 90-second period of the application was traced. As mentioned earlier, the RMV file sizes are quite small. This trace is 25 megabytes on disk. As shown in the area highlighted in green, the allocations increase over time as the various resources are loaded. The allocations are color-coded for us by type using the color key displayed under the graph. It is clear from the coloring in this example that the majority of the allocations after the initial startup period are textures which are colored in orange followed by multi-use buffers in light purple and render targets in pink. No problem if you don't like the default color palette, you can easily change the colors in the settings. When moving the mouse along the graph, a pop-up displays the total allocated memory for each of the live resource types at that point in time. To get more details about a specific point in time, the user needs to create a snapshot. Snapshots are points in time that we can dive into for detailed information about the memory state. Snapshots are created by right-clicking on the point of interest and selecting the pop-up menu item. Each snapshot is recorded in the table below the graph. I'm going to make a couple more, one each for the 3 main plateaus in the timeline. Now we have 3 snapshots at interesting places in the trace. Each snapshot is saved automatically into the trace file on disk so that the next time we open the trace we can revisit the same point in time. Snapshots can be renamed or deleted by right-clicking on them in the table and using the pop-up context menu. Let's look in more detail at snapshot 2. To do this, simply double-click on it in the table. The snapshot is opened in the Heap Overview window. This is one of the 6 summary windows that we can see down the left-hand side of the UI. The Heap Overview window displays information about the physical heaps available in the hardware and summaries of their usage. Starting at the top of the view is the local heap, which exists on the GPU and is visible to the CPU. We can immediately see that there is a warning stating that this heap is oversubscribed. The requested bar is coloured in red to indicate the oversubscription. Depending on how the resources are being used and the resulting page migrations caused by the oversubscription, we might want to investigate this further. In the centre we can see the physical description of the heap's memory properties, along with the smallest, largest and mean allocation sizes. The circle graph on the right gives us a breakdown of the resource usage by type, where we can see that the descriptors make up most of this heap. The invisible heap is next and represents the main GPU memory that is invisible to the CPU. Here we can see that we have budgeted well within the physical heap's limits, as the requested bar is in green. At the bottom we have the host system heap with similar information. Using the information in the heap overview, we are able to start answering some of the questions we set out earlier. A combination of the local and invisible heap information enables us to answer question number 1, which is, how much VRAM am I using? We have already answered question number 2, as we can clearly see the warning about the local heap being oversubscribed. Now let's take a look at the resource overview window. The resource overview allows us to visualize the resources as a block chart, which can be configured to reveal lots of useful information. At the top there are 6 pull-down menus that allow us to sort and display the data in ways that can help you identify memory usage problems. Below this we have useful summaries including the remaining memory available, the allocated and bound total, the allocated and unbound total, and the number of allocations and resources. In the main block chart, the resources are sorted spatially so that the largest allocations are at the top left corner, stepping down to the smallest allocation in the bottom right. A resource can be selected by clicking on it in the block chart, and the details are displayed at the bottom of the view. The preferred heap drop-down list allows you to include resources based on their original preferred heap. You can use these settings to customize which heaps are included in the block chart. The resource usage pull-down allows us to control which resource types are displayed in the view. As you can see, by using the pull-down, it is possible to focus on a specific resource type within a preferred heap very quickly. The color by pull-down allows us to color the resources based on one of their properties, such as resource usage, allocation age, or bind time, and more. The default selection is to color the resources by usage type, which we will leave selected for now. On the right-hand side, there are 3 pull-downs that control how the data is sliced or grouped. This allows us to group resources together based on their properties. There are 3 levels of slicing controls, which allow us to nest groupings, giving you fine-grained control over how the data is displayed. Before we start using the controls, we can now answer question number 3. Which are my biggest resources? With the current pull-down settings, the biggest resources are at the top left. Clicking on a resource will display basic information about the resource below the block chart. Here we can see the selected resource is a multi-use buffer, its size, resource ID and allocation ID. Let's take a closer look at the colouring options, as these can reveal very interesting information. The Color by Allocation Age option displays the resources using an intensity scale, with the oldest resources appearing darker and the younger resources appearing lighter. Colouring by preferred heap displays the resources using colours that represent the preferred heap intended by the developer. A resource may not end up in its preferred destination for a number of reasons, and it's important that we can easily identify cases where this is happening. The Colour by Not All in Preferred Heap option allows us to quickly identify which resources are currently not in their preferred heap. They are shown here in pink. We can clearly see that 4 of the largest resources, a few mid-sized resources, and a few small resources are currently not in their preferred heap. We can use the Level 1 slicing pull-down to group all of the resources not in their preferred heap into an area on their own. All of the resources not in the preferred heap are now grouped in a block on the right-hand side coloured in pink. We can go one step further and recolour the resources by their usage type. Now if we look at the resources that are not in their preferred heap, we can see that they consist mostly of multi-use buffers and a few textures. Being able to group and colour resources by their properties is a powerful way to interpret the memory trace data. RMV allows you to discover in just a few minutes what used to take days, if not longer. Let's move on to the allocation overview. Each allocation is now represented by a coloured bar whose width is proportional to the size of the memory allocation. In this view we can quickly see the largest allocations at the top of the list and therefore answer question number 4. This trace is from a different game than the previous slides, and its largest allocation is actually a depth stencil buffer. There is a useful toggle at the top of the UI that allows us to normalize the allocation widths. Now we can see the allocations that contain place resources in more detail. The dense black areas indicate areas of memory that contain many small sub-allocations. A nice feature of this view is that we can also sort the allocations by properties other than size. The Sort by Fragmentation Score sorting option can give us more information on how efficiently we are sub-allocating. The allocation with the most sub-allocations is now at the top of the list. From the information shown, we can start to answer how efficiently we are sub-allocating and answer question 5. One thing we want to watch out for is the unbound memory in grey between resources. The unbound areas are wasted memory caused by padding and the algorithm being used to place resources within the allocation. We can double-click on an individual allocation to view more detail using the Allocation Explorer. The Allocation Explorer allows us to inspect each allocation and dig a little deeper into each of the resources they contain. At the top of the view is a list of all the allocations in the trace, and because we jumped here from the allocation overview, the same allocation has been selected for us. There is a lot of useful information in the table, including the allocation size, the bound and unbound amounts, the preferred heaps, the amounts committed in each heap, and the unmapped amounts. All columns are sortable. In the middle section we can see the resources contained in the allocation, and at the bottom of the view there is a list of the same resources with more details about the current memory properties. To get more details about an individual resource, we can double-click on a resource to open it in the Resource Details view. At the top of the view, we can find the properties of the selected resource. This includes the preferred heap, create flags, unmapped percentage, commit type, image type, dimensions, format, swizzle, and much more. To the right, the circle graph shows its current physical residency. In the center there's a timeline displaying the life cycle of the resource in terms of memory events. The colored icons in the timeline represent the events contained in the resource events list below. These events include timings for the resource's creation, virtual memory allocation, binding, and physical memory mapping to VRAM. The events in the resource list allow us to answer question number 6. When did my resources get uploaded? We jumped over the resource list view, so let's go back and take a look at what it can do for us. Along the top there is a ribbon of summary graphs. These show statistics on the resource type counts, requested virtual memory, committed virtual memory, allocation size histogram, and virtual memory usage. All of the resources in the memory trace are accessible in the list below the ribbon. The list can be sorted by any of the column headers. For example, if we sort the list by preferred heap, we can see that some of the resources are orphaned, which is not a good thing. This means that their parent allocation has been removed, leaving these resources at risk from having their underlying memory overwritten. Another way of locating orphans is to use the search bar in the top right. The search is applied to all the fields in the table and quickly locates the orphans for us. So that took care of question 7 for us and found a memory issue that we really should go and fix. Let's try to answer question number 8. Are there any unbound or unused resources? Unbound resources are not displayed in the allocation overview by default. You can display them by selecting the unbound options in the Resource Usage pull-down menu. The unbound resources are now shown. Let's take a look at a couple of them by double-clicking on them. In our first example of an unbound allocation, we can see that it is 2 megabytes in size, has 0 bytes bound, leaving 2 megabytes unbound, and contains no placed resources. In our second example of an unbound allocation, we can see that it is 16 megabytes in size, has 14.85 megabytes bound, leaving 1.15 megabytes unbound, and it contains 49 resources, and some of them are unbound. Let's move on to question 9. In which heap did my allocation end up in? We already know how to identify the resources which are not in their preferred heap by using the Color by pull-down to select the appropriate color mode. The salmon pink resources are not in their preferred heap, and we can find out where they ended up by viewing them in the Resource Details view. To do this, simply double-click on the resource of interest. Okay, so here are the resource details. In the summary on the left, we can see that the preferred heap was local, and below that, there is a very clear no in the fully mapped in preferred field. On the right hand side in the physical residency circle graph there is a warning pointing out that not all of the resources within its preferred heap. Instead of being in local memory, 94% of the resource is in host memory and just under 6% is unmapped. To understand a little more about the intention of this resource, we can look at other properties, in particular its usage flags, and we can also look at the resource events in the list below. Scrolling to the bottom of the list, we can see that the memory was used early in the trace for about 10 milliseconds, idle for another 10 seconds, and then unmapped. The last feature that I want to talk about is Snapshot Compare. This allows us to compare two snapshots and generate memory usage deltas that can be useful in detecting resource leaks. In this example, the trace is 10 seconds in length and is comprised of two scenes that contain different resources. Scene 1 is 5 seconds long, as is Scene 2. I'm a little suspicious because I know Scene 2 should be using fewer resources and consume less virtual memory, but this does not seem to be reflected in the height of the graph. To investigate this, I create two snapshots, one in each of the scenes. I then select both of the snapshots from the list, right-click, and select Compare Snapshots. This opens the Snapshot Compare view, which has been designed to reveal the memory usage deltas between the two snapshots. Along the top of the view is a ribbon with summaries of the deltas. Bars shown in green indicate an increase in delta values, and bars in red would show a decrease. Below the ribbon are summaries for each of the heaps, showing increases with green triangles and decreases with red triangles. In this delta summary, we can clearly see that in Snapshot 2, the bound virtual memory has increased, there are 10 more allocations and 20 more resources. In this case, it's starting to look like we're not releasing the resources used in Scene 1. To dig deeper, we can use the Memory Leak Finder button, highlighted in green on the left. Along the top of the view, we have 3 toggle switches that allow us to display combinations of resources from the two different snapshots. Below each toggle switch is the resource count and memory usage amounts for the resources in that group. By default, the resources that are present in both snapshots are shown, as seen in this screenshot. We can deselect the common resources and select just the resources unique to snapshot 0. This is where it's important to know a little bit about the structure of your app in order to interpret the results. In this case, I know there should be more than 20 unique resources in Snapshot 1, as this scene has many more elements. From the timeline graph, I would also have expected the memory usage drop in the second half of the memory trace. Given this information, I can be pretty certain that resources from Snapshot 1 are also present in Snapshot 2, and we're leaking memory. So it's time to go off and fix the problem, restart the application, and take another RMV trace. Sure enough, in the latest trace we can see a drop in allocations just around the 5-second mark, which is what I would have expected to see. I've added 2 snapshots before and after the 5-second mark and can now generate another comparison. This time we see plenty of red in the delta graphs, indicating a reduction in virtual memory and resource usage. We can also clearly see the amount of memory recovered and a reduction in the number of allocations and resources being used. The Snapshot Compare tool allows us to answer our final question: did I forget to remove resources when no longer needed? So that wraps it up for RMV. I hope you've enjoyed this presentation. You can find out more at GPU Open and download RMV directly from GitHub using the links below.